Hello Calc 3, welcome back for the second half of the videos on section 12.5. In the second half of section 12.5, the book covers the concept of planes in space. So in the last video we talked about lines in space. This video we will talk about planes in space. So remember from the last video that to specify a particular line in space, it sufficed to give two pieces of information. For the line, it sufficed to give any point that was on the line and then a vector that was parallel to the line. For planes in space, to specify what plane we're talking about, it suffices to give two pieces of information again, but this time we need any point in our plane, and then instead of a vector parallel to a plane, we need a vector that is normal or perpendicular to the plane. So the vector that is normal to the plane in some sense describes the tilt of the plane. So look down at the diagram that I have taken from the book here. The normal vector is the vector in red, and the plane is the kind of grayish rectangle. So notice that the normal vector is coming out of the plane, directly out of the plane. And we also have some arbitrary point inside of our plane, which is denoted P0. And now we want to work on developing the equation for a plane, a way to represent the plane. Similar to the way we did for the line, we're going to have a vector equation and then a component equation in this case. So let's work on developing those equations. Let's start off by letting M be some arbitrary plane that passes through the point P0 with a normal vector, which we're going to call N, and in component form that normal vector is going to be A, B, C. So again, you can still look at the diagram that I have in the upper left here while we're going through this. Then the point, or I should say a point P, with coordinates x, y, z, is on our plane M if and only if the vector that goes from P0 to P is perpendicular or orthogonal to the normal vector N. All right, so I'll say that again. A point with the coordinates x, y, z is on the plane M if and only if the vector that goes from P0 to P is perpendicular or orthogonal to the normal vector N. But as we said, I think in section 12.3, our vector P0P is only orthogonal to the vector N if the dot product of the two vectors is equal to 0. So that's a fact that we learned in section 12.3. And so we can use this fact to give ourselves an equation for the plane. So assume that the vector from P0 to P dotted with the vector N is equal to 0. Then if we write our vectors in component form, we get that P0 to P is equal to x minus x0, y minus y0, and z minus z0. And the normal vector is A, B, C in component form. And we know that when we dot these two vectors together, we should get 0. And now we're going to apply the definition of the dot product. So we find that A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. So the plane, or plane M, consists of all points satisfying the equation a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. And this leads us right into our first big discovery for this section, which is the equation for a plane. So if we have a plane that passes through the point P0 and it is normal to the vector N with component form A, B, C, then our plane, we have a few different equations that we can write down for our plane. The first one is a vector equation, which is just the equation that N, or the dot product of N and the vector from P0 to P is equal to 0, which we had written up here. The second equation is called the component equation, and this is the equation that we ultimately derived here, which is the plane can be expressed with the equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. And then this last equation representing our plane just takes the component equation above and it simplifies it. So in that case, we can distribute a, b, and c through x minus x naught, y minus y naught, and z minus z naught respectively. And we end up with the equation a times x plus b times y plus c times z is equal to d, where d is equal to a times x naught plus b times y naught plus c times z naught. That's just using a little bit of algebra from the component equation above. The nice part about the simplified component equation is that it's very easy to tell right away what the vector normal to our plane will be. And oftentimes in examples, the planes will be represented with a simplified component equation, something that looks like this. Okay, let's go through our first example where we're finding an equation for the plane that passes through 3 different points. In this case, we have the points A, B, and C, which are given with the ordered triples listed up here. So to find an equation for the plane, there are 2 pieces of information that we need. We need a point that is on the plane, and we need a vector normal to the plane. So it's easy to find a point on the plane since we're finding the plane that passes through the 3 points that are given to us. So we can just choose the point A to be the point that we'll use to calculate the equation of the plane. And now we need to find a vector that is normal to the plane passing through A, B, and C. Well, we can construct vectors inside of this plane using the points that are given to us. So the vector AB is going to be in the plane, and the vector AC will also be in the plane. And that means that if we take the cross product of those 2 vectors, so we take the cross product of the vector from A to B and the vector from A to C, then this cross product is going to be normal to our plane. So if we can find that cross product, that'll give us the second piece of the puzzle here, the normal vector that we need. So first we're going to write the vector from A to B in component form, and we find that it is equal to 2, 0, minus 1. And we can also write AC in component form, and we find that that is equal to 0, 3, minus 1. And now we want to calculate the cross product of our 2 vectors. So we calculate the determinant of this 3 by 3 matrix that is given here. And with a little bit more calculation, we end up finding that the cross product of AB and AC is equal to the vector 3i plus 2j plus 6k. So now we have both pieces that we need to write down the equation for the plane. We have both a point on the plane, which is given by the point A, and now we have a vector that is normal to the plane given by the vector 3i plus 2j plus 6k. And we can just write down right from here the component equation of the plane. So we end up getting 3 times x minus 0 plus 2 times y minus 0 plus 6 times z minus 1 is equal to 0, where the 3, the 2, and the 6 are coming from the normal vector that we just found, and the 0, 0, and 1 are coming from the point that we selected, which is our point A. And this will give us the equation for the plane, and if we wanted to, we could also write the simplified component equation just by doing a little bit of algebra to the equation above, distributing some constants and then moving things around. And in that case, we end up finding that the plane can be represented by the equation 3x plus 2y plus 6z is equal to 6. Okay, so let's move on to a bit of a different topic now. So 2 planes are going to be called parallel if their normal vectors are parallel. And two planes that are not parallel will always intersect in a line, which you can see in the diagram that I've conveniently taken from the book here. We have a plane that is kind of pink, I guess, and then a blue plane. They are not parallel to one another, and so they intersect, and they intersect at this black line that is drawn in the picture. And notice in the diagram that the line of intersection is orthogonal to both of the normal vectors. And for this reason, the intersection line is going to be parallel to the cross product of U1, or excuse me, that's an N1 and N2, right? Because we know that the cross product is going to be orthogonal to both N1 and N2, and we can see that the line of intersection is orthogonal to N1 and N2. So that means that the line of intersection is going to have the same direction as the cross product of N1 and N2. So keep that in mind as we go into this next example. So let's say we want to find parametric equations for the line in which two planes intersect. And the two planes are given by the equations 3x minus 6y minus 2z is equal to 15, and 2x plus y minus 2z is equal to 5. So to find the line, we need two pieces of information. Remember, two pieces of information are needed. We need a point that lies on the line, and we need a vector parallel with the line. So we already said that the line of intersection, the line that we want to find, is going to be parallel to the cross product of the normal vector for our first plane and the normal vector for our second plane. Now, reading the equations for the planes, we know that the normal vector for the first plane is going to be in component form 3, negative 6, negative 2. And the normal vector for our second plane in component form is going to be 2, 1, negative 2. And now we can just find the cross product of these two normal vectors, and that will give us a vector parallel to our line of intersection. So moving down here, to find the cross product of N1 and N2, we set up the matrix IJK, 3 minus 6 minus 2, 2, 1 minus 2, and we want to find the determinant of this matrix. And so that'll break down into 3 smaller 2 by 2 matrices. Hopefully you're familiar with this process by now from calculating cross products in section 12.4. And after doing some calculation, we end up finding that the cross product of the two normal vectors is going to be equal to 14i plus 2j plus 15k. So this vector right here is going to be a vector parallel to our line of intersection. So that's the first piece of information we need. And now we need a point that lies on the line of intersection. So any point that lies on the line of intersection is going to be a point that satisfies both equations. Right? By definition, the line of intersection is the set of points that satisfies both the equation for the first plane, this equation, and the equation for the second plane. So let's see if we can find a point that satisfies both of those equations. Well, there are a ton of different points that satisfy the equation, but we might as well just try and find the z-intercept. So to simplify our problem here, we can let z equal 0 right off the bat and try and find a point that satisfies both equations such that the z component of our point is equal to 0. So we're going to assume that z equals 0 and then see what happens to the equations for the planes given above. And so both of these equations for the planes, we can just get rid of the z term in both equations, and we end up with the two equations 3x minus 6y is equal to 15 and 2x plus y is equal to 5. And now this is just a system of linear equations. We have two equations and two unknowns, and we want to solve for both of those unknowns. So if we multiply our second equation by 6, and then we add the two equations together, the y terms are going to cancel, and we end up with the equation 15x is equal to 45, and that will imply that x is equal to 3. And after we know that x is equal to 3, we can just plug it back into either one of the equations up above, and we find that y is equal to -1. So if that was a little bit fast, how we solved the system of linear equations there, you can just pause the video here, write down both of these equations, 3x minus 6y equals 15 and 2x plus y equals 5, and solve the system of linear equations for yourself, because I did kind of briefly go over the calculation that's being done there. And after we have found our x-coordinate and our y-coordinate, we can conclude that the point 3, -1, 0 is on our line of intersection. And so now we have both pieces of information we need to write down the parametric equations for the line of intersection. We have our vector parallel to the line, and now we have our point that lies on the line. And so from here we can just write down the parametric equations. The 3, -1, and the 0 that isn't written for z but would go right there are going to be taken from our point that lies on the line, and then the coefficients for t, the 14, 2, and 15 are going to be taken from the vector that we calculated here, that we know is parallel to our line of intersection, and ultimately we end up with the parametric equations x is equal to 3 plus 14t, y is equal to -1 plus 2t, and z is equal to 15t, where t is ranging from -infinity to infinity. Okay, so let's move on to, I think, the last topic for section 12.5. Remember that in the last video, we found a formula to calculate the distance from a point to a line. And here we want to find a formula for the distance from a point to a plane as opposed to a line. So let S be some arbitrary point in space, and let P be any point on the plane in question here. Then the distance from S to the plane is given by this formula here. So the distance is represented by the letter D, and it's equal to the magnitude of the dot product between the vector from P to S and the direction vector of the normal vector associated with our plane. Okay, so I wrote down here where n is a vector that's normal to the plane. And let's just put this, this formula right into practice with an example. So let's say we want to find the distance from our point S, which is given by the coordinates 1, 1, 3, to the plane 3x plus 2y plus 6z is equal to 6. So to find the distance, we need a few pieces of information. We need some point in the plane so that we can find this vector from P to S. And we also need a normal vector to the plane. So the vector normal to the plane is pretty easy to find right away. So we can look at the equation that's given to us here for the plane and read right off of there that the vector normal to the plane can be written in component form as 3, 2, 6, or I should say a vector normal to the plane is the vector in component form 3, 2, 6. And now we want a point on the plane. So we need to find our point P. And similar to the method we used in the previous example, we can simplify this problem a little bit just by letting z equal 0 and letting y equal 0 in our equation for the plane here, and then solving for x. And as long as we can find an x value that satisfies that equation when z and y are equal to 0, then that point is going to be on the plane. So if we let z equal 0 and y equal 0, we're left with the equation 3x is equal to 6, which implies that x equals 2. So the point 2, 0, 0 will lie on our plane. And now we have, I think, all of the information apart from some vector operations we have to do now to calculate the distance. So so the distance is given by the magnitude of p to s dot producted with n over the magnitude of n. And we can find the component form for our vector from p to s. And we end up finding that that is equal to -1, 1, 3. And we want to find the magnitude of our vector n as well. So we take the components of n, we square each of them and add them together, and then take the square root, and we end up finding that the magnitude of n is equal to 7. And now we actually have all of the information we need. So again, the distance is equal to this magnitude given here. We just found the component form for the vector from p to s. So we write it here as -1, 1, 3. And we're going to take the dot product of that vector with the normal vector that we found, which is in component form 3, 2, 6. And then divide by the magnitude of n, which is 7. We end up finding that this dot product is equal to 17, and then we can divide by 7. And so ultimately the distance from our point S to the plane that was described by the equation above is equal to 17/7. And then just a little tidbit of information at the end of section 12.5 here. So we already talked about the angle between vectors in the plane. We can also define the angle between, or I should say the angle between vectors in space. We can also talk about the angle between two planes in space. So the angle between two planes is defined to be the angle between the vectors that are normal to each plane. So if we have two planes, we want to find a vector n1 that is normal to the first plane, and then we find a vector n2 that is normal to the second plane, and the angle between n1 and n2 will be the angle between the planes m1 and m2. And we already derived a formula for finding the angle between two vectors. So ultimately, the angle between our two planes m1 and m2 is going to be given by theta, and that will equal the inverse cosine of the dot product of n1 and n2 divided by the magnitudes of n1 and n2. All right, so that is all the information for section 12.5, and more than just that, it's actually all of the information for the material that we will be covering in section 12. So from here, we will be moving on to section 13 and doing some calculus with vectors. So look forward to those videos coming up in the next few days.